So I just wanted to check with you, how you're all following the course so far, and then how you perceive the difficulty of this course or the lecture materials as well as the lab materials. So is there any feedback? Because I have actually heard some feedback via some other channels that this course is considered to be difficult, which was a bit surprising. But I guess me being a teacher, I guess I'm supposed to find this material easy. Otherwise, I wouldn't be able to teach. So, is there any kind of particular feedback or anything like that that you want to share? Or that always helps. We get kind of sense of what is the speed at which I deliver the materials, and also, in fact, the listening to others or the sharing how you feel about the course with the other students in the lecture hall can actually help you as well as the others know that I think not everyone is finding it easy, or not everyone is finding it difficult. So if you have any thoughts, do feel free to share with all of us. Actually.
Yeah, I feel like some of the questions in the quiz are a bit of ambiguous in terms of whether the wording or like the assumptions that it made. And because every quiz is kind of taking up a large percentage of the grade, so that can make up a little bit of this.
I see. Well, it's only 8%, right? So I wouldn't call it a large, but you're right. So but we're going to look into each quiz questions more carefully from next time. Yes, there are we do acknowledge that there are some ambiguities or some of the kind of implicit assumptions that were made. We'll try to make it more clear from going forward. Okay, that's noted. I do see that some of the course assistants are on Zoom, so they should make a note of it.
Yeah, I just had one comment. I think the lectures, when you're teaching them, are very, at least to me, I'm able to follow them. But one thing that I've always liked to do is to be able to pre-read the content and learn about it a little bit myself before I'm seeing it live. Right. Sometimes I have trouble following things when I'm seeing it for the first time. I know you have the syllabus, I know you have the lecture notes, and I know you have some recommended resources. Sometimes it's a little bit hard to triangulate where should I really be reading among all those sources to really prepare myself for the lecture. So personally, I found if there was a mapping to say this week, recommended readings, these chapters, I think that would at least personally help you prepare for the actual lecture.
That makes sense. So most of the materials for each of the week, I actually finished preparing them half an hour. That's often the reason why I don't have the materials uploaded in advance. But that's a good point. I'll try to do that more often from going forward. Okay, all right, that's a good suggestion. Any other suggestions or feedback? Oh, it's all good. All right, good. So today, let's recall what we learned so far, because we're kind of taking one step up in terms of more of the mathematical analysis, and then we're getting closer to the more modern, let's say, natural language processing. And one thing we have learned until last week was how to build a neural network that is able to handle a variable length sequence without any bound on the maximum length. All right, so we learn how to build a recurrent neural network that is able to handle a sequence of the unbounded length, right? In fact, what we learned is that if you forget about the learning part, right? If you forget about the learning part, and if you just apply this recurrent neural network that we have parameterized as a very simple neural network, right? That takes as input previous hidden state and the current observation. So the current times the observation. Then you could just compress it into a single vector, and then you can just apply the same thing over and over. And then you could just go on and on, right? So there was no reason to stop at any point as long as there is a new input coming in. And that was a pretty good thing, but what were the few things that we noticed there is that so the number of the parameters is constant with respect to the size of the input. That was really nice, because in the feedforward neural probabilistic language model that we talked about right before, the number of parameters tended to grow with respect to the size of the input. then that wasn't good, right? Because the number of parameters goes too fast, and then this effectively means that you're going to have a fewer data points per parameter, and then that means that you can't really estimate those parameters correctly or well enough. Okay. And then another thing that we'll notice was that in order to train this recurrent neural network on the problem language modeling, what we ended up with was a very, very deep neural network. Although yeah, it's always a kind of there's a symmetry, right? So either you process a very long sequence, or you're going to input a fixed size vector and then make it go through many, many layers. They're essentially effectively the same thing, right? So then you start wonder whether it makes sense to train the kinds of recurrent networks. So, and then if you think about it, it has to be a bit difficult. Why is it difficult? Let's just think about quickly, bring the thought experiments about what the backpropagation procedure that we have learned actually does. So if you imagine that there's just a one neuron, okay, so we're going to do the binary classification. So there will be one scalar that is output by our neural network. Then we're going to pass the value through the signal function, and then we can get the probability of the class, probability of this input belonging to the positive class. We can compute that one, right? Then now, let's say this was just linear. Let's say we had a one hidden layer here. Okay, so there was a one hidden layer. And then what happens is that in the hidden layer, we have many neurons or the units, however you call it. And each one of them is going to output a scalar value. So the scalar value can be, let's say, some value between -1 and 1 if you use the hyperbolic tangent nonlinear function, can be just some positive value, or the non-negative value if you use a rectified linear units. Okay, each and every neuron is sending a message, and then the message is going to be multiplied with the so-called synaptic weight. And then what is the synaptic weight? That is in fact the class embedding, right? So one of the dimensions of the class embedding. So we had the hidden vector H, or the phi of x. So there was a feature of the input, and the phi of x was, let's say, multidimensional. So you can imagine that each and one of them is a neuron sending out a single scalar. And then what did we do? We computed the dot product between this phi of x and the class embedding vector. That is the same dimensional, right? Now what that means is that we're going to multiply the message or the scalar value that has been sent by one neuron with the corresponding weight value in this class embedding. And then we're going to just sum them up later on. So we're taking the weighted sum of all the values coming out of neuron. And then what we do is that we are going to compute the loss function, loss value. And then what was our loss? Is a negative log probability of the correct class. And then what we do is we're going to now compute the derivative and then do the backpropagation. Now, when you do so, what you notice is that this gradient that you compute, so gradient with respect to the hidden vector, so phi of x, right, is effectively doing what we call credit assignment. What is a credit assignment? We're trying to figure out what was the value of each neuron. So what should have been the output of each neuron in order for the loss value to go down. Or if we compute the gradient, okay, negative gradient, right? So that's what we're finding. What that means is that we are going to, let's say that we're assigning the credit as well as the blame. So if the value of the neurons, let's say output needs to go up, we say that, okay, so there was a credit. If the value of that hidden neurons output should go down, that's the blame, right? So this whole process of backpropagation, you can imagine is a credit assignment procedure. And if you think about it, just very intuitively, let's say you look at the one hidden layer, one layer. You can imagine that you know what are the neurons that are making a big mistake. If I notice that the loss is really large, then what would be the neuron that I would penalize first? The neuron that has high weight associated with it, or the high value that came out of it, right? So whatever the neuron says, okay, here's a high value. Let's say big scalar I'm sending, and then eventually my loss was really high. Then the neuron is probably doing something wrong that sent us a message that led to my loss value being really, really high. So then I would say, okay, we need to lower the value down, right? if there was, and then now you can imagine how this process goes on, and then computing the gradient is precisely doing this credit sum. But let's say you need to do that for many layers. So we have built a very deep neural network, or we have run the recurrent neural network that processes a very long sequence, and then we have a loss value at the very end. And now I need to figure out whether one of the neurons, let's say 100 steps earlier, or the 100 layers before, was contributing positively or negatively to the final loss value. Intuitively, it's difficult, right? Because I need to see which of the neurons in the next layer that neuron actually impacted and how it has impacted. And then, of course, that one still doesn't tell me what the impact on the loss value was. So I'm going to say, okay, I'm going to chain it out. So this one has impacted all the next layers neurons in this way. And I need to go follow through, and then trying to track back to see what was the actual impact of this hidden neuron 100 layers before on the final loss value. So it turned out this intuition actually works perfectly, and then the actual backpropagation procedure tends to fail in two dramatic ways. And both of the ways, we're going to look at it now carefully. Now to do that, we need to set up a bit simpler scenario than the recurrent language model that we talked about last week. The reason why it's going to be, why we're trying to simplify the whole thing is in the last week's lecture, we had the loss value coming out of every step, right? Every point in the sequence. But we don't want to do that. There are too many loss functions to look into. So we're going to just look at a text classification problem that we looked at in the very first lecture, right? But instead of using a continuous backover, we're going to use a recurrent neural network. Recurrent neural net that's going to read the sequence one word at a time, all the way to the end. And then based on the vector we get, because we learned last week that this vector is a summary or the lossy compressed version of the entire sequence. And then based on that, we're going to try to classify that into one of the classes. So let's see. So let's set up the whole thing. We're going to assume that we have a sequence of length capital T. And then we're going to say that these the things can be just real values actually for the simplicity's sake as well. So xt is going to be just d-dimensional vector. It's a bit of a departure from what we've been doing last week. Until last week, we said that the xt is a one-hot vector. But then if you think about it, one-hot vector is also a real value vector as well. So we don't have to worry too much about this at this point. And what we're going to do is we're going to solve the problem of sequence classification or regression. So it's different from language model. And then the interesting thing is that in this particular case, you can imagine a very, very deep neural network, but all the layers are tied. So the output of this network, f of x, is going to be r times some nonlinearity applied to the final word or the input times u, that's going to be the recurrent weight, times this nonlinearity w times xt minus 1 plus u times another nonlinearity, and we go on and on and on until the very first one. So H0, we need to have H0, and then we said that often this is just all zero vectors, but we can learn that as well if you want. And I need to just be careful closing all the brackets. Right?
The particle d on wx, particle d minus 1. Sorry, where is that? This one? Second one? Second one. Yeah, that's
capital T minus 1, yes. So that's going to be x capital T minus 1. Thank you. So this is our neural network. This, depending on how you want to view it, this is just a feedforward neural network with a depth T, capital T, or it's just a recurrent neural network that has just processed the sequence of length T.
Sorry to interrupt, but
yeah,
you start the recording?
Oh, yeah, it is being recorded.
Is it okay?
Let's double check. Yep, it is being recorded. So, and then another way to write it is that the f of x is r times ht plus c, where ht is going to be sigmoid of or the sigmoidality, some kind of nonlinearity of wxt plus uht minus 1 plus b. So this is just same thing, right? You know, we're just rewriting into a slightly simpler format that resembles the recurrent network that we have learned. And what we're going to do is we're going to say we are doing the regression. We'll do the regression, and then we're going to use the L2 loss. So our loss function is going to be f of x minus y squared. Now, why are we using this instead of the negative log probability as a loss function? It turned out that this is exactly the negative log probability of the Gaussian distribution with variance 1, and then our covariance, well, in this case, identity covariance. So it's all the same thing. So we're sticking to it. Only thing that we're saying is that what this neural net is trying to output is some kind of real value vector. And then we always have the target real value vector y star or y as well. Now then, let's recall what we learned about the backpropagation. And then in the case of the recurrent neural network that actually processes a sequence, and then we often assume that the sequence is following the time. So you can imagine some kind of time series. So thereby we call it backpropagation through time. So let's see. So what do we need to compute? Let's look at this whole thing carefully, and then let's look at this loss. So the DL, DR. So we should be able to compute this, right? So L is the loss, and then R is the very final, let's say, range matrix. And then this one is going to be DL, DF. So we are computing the derivative of the loss function with respect to our function at first. So then whatever comes out of that times df and dr. So we need to compute this in order to compute that. Right? So we have a number of parameters here. What are those parameters? We have r and w and u, b, and c. So we have all these parameters. And then the first thing we're trying to look at is that what is the gradient of this loss function with respect to the very final weight matrix R. And then, yeah, of course, it has to be kind of gradient, so nabla symbol, but I'm going to just do this partial derivative just because that's much easier to write. And then it's much more intuitive. And to do that, because we have learned about the chain law of derivative, we're going to compute the gradient of L with respect to whatever our neural net has predicted. And then we multiply that with the Jacobian of the whatever our neural net has predicted with respect to the R matrix. Similarly, what is the next one? The next one we need is the gradient of L, the loss function, with respect to our bias vector C. And then this one will do the same thing. And what was the idea of the backpropagation? The idea of backpropagation is that we can always share these computations. So we're not going to compute this gradient of the loss function with respect to the output of the neural network. Every time we compute the gradient of the loss function with respect to each and every parameters, but whenever we can share, we're going to share. That's the idea of the backpropagation. So that's done. Now let's go to the next one. Perhaps we can go to this transition matrix U. And here, I'm going to actually introduce a slightly different notation for the purpose of easy, let's say, drawings. I'm going to duplicate. Now let's see. All right, so let's see. R, W, U, then C, then plus B. Now what I'm going to do is I'm going to rewrite it a bit in a sense that I'll say this is the W matrix. We have W matrix that is applied at the teeth times that or the teeth layer, right? And then here U as well, the very same thing, T. But this W is at T minus 1 step, and this U is at T minus 1 step. Then this U is at the very first one. This U is at the very first one, and then this B is at the very first one. This B is at the T minus 1. This B T, and then C. just to make the kind of derivation of the simpler, and then to make it much more explicit that this W and U and V are used over and over. It's the same copy used over and over. Now, in this case, what we now need is to try to compute the gradient of the loss function with respect to U. And then here, the same thing, gradient of the loss function with respect to F. And then this one, what happens? Very same thing. Sure, the computation times, we go over time. So we're going to go through one layer at a time, going back from the very final layer. Then we look at the gradient of the loss function. Oops, I'm sorry, not the loss function. So the gradient, or Jacobian of the prediction of our function F, right? The prediction of our neural network with respect to, let's look here, HT. With respect to HT. What is the HT? HT is what comes out of each of the layers. Right? HT is what comes out of each of the layers. And then this term is effectively what we just talked about earlier in the intuitive picture about the credit sum. We want to know how each and every neuron in the Tth layer affected the prediction of this neural network. So what does this Jacobian tells us that had I changed one of the values in this HT, what happens to the actual prediction of the neural network? Okay? So that's just a definition of the gradient or the Jacobian derivative, however you call it. And then we compute now the Jacobian of HT with respect to the application of this U matrix at time step t. So this is what we talked about last week quickly, and then all of you actually knew about it perfectly, so we didn't actually go through it. The idea is that if we use the parameters, so it's the same parameter over and over, we just compute the gradient of the loss function with respect to each and every application of those parameters, and then just sum them in order to get the gradient of the loss function with respect to that particular parameter. All right, and then we can do the exactly same thing for W as well. So we compute, we're going to not compute, we're going to just share the computation of the DL, DF. Then we go through each and every layer, and we look at how the output of the layer impacts the prediction of the neural network. Then we look at how the application of this W matrix at time step t impacts the output of the layer time step t. We do the exactly same thing for bias as well. All right, so let's see what are being shared. Okay, so we shared all those computations there. Next up, we're going to share all these computations. So, in fact, there are a lot of, let's say, the Jacobians that have been computed, but most of those Jacobians are in fact shared across all those parameters. All right, so far so good. What this actually says is that one of the key things here that we want to look into is this term. Why is that term, let's say, important? So this term, you can actually compute it yourself very easily. I can tell you it's going to be the 2 times the f of x minus y. Now, these ones are very, very easy to compute. This one, I can tell you already, is going to be the derivative. So the derivative of the pointwise nonlinearity times the linear term. So in this case, just 1. In this case, actually ht minus 1 is going to be xt, and then this one is going to be ht minus 1. But this one is a bit tricky. It's not easy to imagine what the output answer of this term is going to look like. Now let's try to rewrite this one. So the df of dht can be written down as df of dht, so the capital T. And then we're going to compute the dht with respect to dht minus 1. And on and on and on until the very end. It's the dht plus 1 with respect to dh. So where does this come from? This comes from the fact fact that the ht is a function of ht minus 1. And then the ht minus 1 is a function of ht minus 2. So in order to compute ht using the ht minus 1, t minus 2, we have to go through ht minus 1. So essentially, what it means is that the influence of the earlier layers onto the future layers have to go through every single intermediate layer. And then the influence is characterized by the Jacobian of the ht plus 1 with respect to ht. If you look here, then what you notice is that we are going to share the computation of all these steps for computing all these summations. So for computing the inner term here, we don't actually have to compute this whole Jacobian independently, separately, and then compute the inner sum. But what we can do is we start from the capital T, then we compute df, dht capital T, and then multiply it against, let's say, dh capital T with let's say, dt capital T. Right? But then next, we go into the t minus 1. And then we can use whatever has been already computed and then simply multiply that with the Jacobian that you compute, that is with ht, capital T with respect to ht, t minus 1. Now, one thing that I'm actually just omitting for the simplicity's sake is that everything here is evaluated at ht minus 1. So that's important to know. Because the Jacobian or the derivative, if you think about it, derivative is just a function. So you need to think about where you actually evaluate this derivative function. So what that means is that we are now propagating the sensitivity to the perturbation backward in time. So this term tells us how sensitive our prediction is with respect to ht, right? H capital T. And this one is telling me how sensitive h capital T is to the change in the h capital T minus 1. Then we're going to multiply that with how sensitive ht capital T minus 1 is to the changes in the ht minus 2. Then we go all the way. We're just propagating back little by little the sensitivity in order to figure out ultimately at time step t or the layer t, what was the thing that I could change in order to make corresponding changes in the prediction of the neural network? This is the credited assignment procedure. Yes.
So for you're talking about just like it's evaluated at ht minus 1.
Mm-hmm.
The next one be evaluated at ht minus 2.
2, yes.
Yeah.
Precisely.
Sorry, I'm not really understanding the summation portion of partials perspective.
Mm-hmm.
So you mentioned that it's related to the Jacobian, but I don't see what the summation of the term out of the Jacobian.
No, it's just actually, so maybe I can put the parentheses to make it clearer. So let me actually take that. This is what I see. Mm-hmm. So of course, it's a summation. So we can always push this inside the summation as well, right? So you can imagine that for each one of these, let's say term within this summation, we're just computing the gradient of or the Jacobian. So the gradient of the loss function with respect to one of the applications of the parameter u or w or v, because they are being used a lot. So that's the reason why we have this bracket with the indexing there. And then all we need to do is just sum all of them to get the gradient of the loss function with respect to the actual original, let's say, parameter u, w, as well as p. Yep. So what are the dimensions of the Jacobian? Is it a Oh, so the Jacobian dimension is actually up to you because now what was the input dimension? Let's say d-dimensional vector. That's what we have assumed. In the case of, let's say, word, then we will say what is the embedding dimensionality, right? So let's say that was d-dimension. And then let's say this recurrent matrix has to be squared because it is using the input as the output from the previous time step. Let's say this was d prime by d prime matrix. then what should be the matrix size of W? It should be D prime by D. And then what should be the size of this B, the bias? It should be just D prime dimensional vector. And then what is the dimensionality of R? Now R is multiplied to this D prime dimensional vector, and then now it depends on what our correct output dimensionality is. Let's call it, let's say D double prime. So this is supposed to be D double prime by D prime. And similarly for C, it's going to be D double prime dimensional vector. All right, any other questions? So this is a pretty useless knowledge, but it gives you a kind of sense of what this backpropagation procedure is, and then what we are actually computing, what we actually mean by learning with the gradient descent. So what gradient gets us, is that what is the right way to perturb our parameters so that the perturbation would lead to the loss value going down, or the going up is gradient, negative gradient is going to go down. And then how do we compute that? How we compute that is that we're going to actually chain or backpropagate this sensitivity. So here what it says is that how should I change our neural net's prediction in order to increase the loss value? Just imagine minus. Okay, let's imagine minus there. How should I change my neural net's prediction in order to lower the loss value? Right, that's the sensitivity, and then with the directionality, and then that one is going to be multiplied with what is the right way to change the hidden layer activation at time step t, capital T, in order to change the F, the prediction of the neural net, and then by chaining them up, now I can tell what is the right way to change this HT, the hidden activation, so that my loss function is going to go down. And then we just train it, and then at each of the layers, we're going to see, okay, then what is the right way to change our parameters in order to change the hidden activation? And then by multiplying it, now I know all the way to the loss function that, okay, what is the direction toward which I need to change my parameters to change my loss function? And then we're just figuring that out over and over. That's what we do. And that is the reason why we call it backpropagation. And before I take another question, so we're going to look at just one of these. So we're going to look at just one of these, which I'm going to refer to as temporal derivative. And the temporal derivative is going to be a Jacobian of the output of the hidden layer at time step t with respect to the input to the time step t. This is a temporal derivative. And if you recall how the definition, I'll actually copy it down there. If you recall this definition here, then this is going to be diagonal matrix of the, I'm using the sigma prime matrix. This is the derivative of this nonlinear function. Now, nonlinear function is applied element-wise, so we just need to look at the derivative. Sigma prime evaluated at AT, I'm going to talk about what AT is, times the U matrix, the transition matrix, where the AT is the input to this nonlinear function. Now this one is also pretty intuitive in a sense. Now what I want to try to figure out first is that how should I change my how should I change A? How should I change A, that is the input to the nonlinear function, so that the output of my nonlinear function changes? And then that's precisely what the derivative does. So this is a derivative. And then once that's done, what do you need to do? We need to figure out how AT, this input to this nonlinear function, changes if I change this U, right? And then it turned out this AT is just a linear function of U. So what we HT minus 1. So what we end up with, sorry about that, is how do I change the HT minus 1 in order to change the value that goes into this nonlinear series AT? And it's just a linear function. And then what linear function says is that this U matrix actually tells us exactly how to change ht minus 1 in order to change the output. That's the idea of linear function, right? So linear function, whatever I do, is going to be linearly reflected on the output. And then what is the reflection, degree of reflection? That is the matrix that's being multiplied. That's the gain. So that's our temporal derivative. This is probably the most interesting thing that interesting concept that we should keep in our mind. So let's just look at one of them. So what would be I think that this could be a bit confusing. So this is going to be, for instance, right, the 0 and 1 if A is, then it might be otherwise, if when sigma of A is a rectified linear unit. Or in the case of hyperbolic tangent, you know how to compute it. It's pretty simple. So what it says is that so in the case of rectified linear unit, what does it say is that we're going to only look at the dimensions of the input into the nonlinear function that were positive. Otherwise, we just ignore. So, it makes sense. Whatever we do, if the value that goes into this rectified linear unit was negative, it doesn't really affect the actual loss function eventually, because it's all zeroed out. Otherwise, it has just a linear input. All right, so far so good. All are following well. Kind of, let's say, curious why we're doing this. I know. So the reason why we're doing it is that my guess is that about 90% of what we're learning today, you'll never need to worry about this ever. But the idea is that we're giving you a degree at some point. So we need to make sure that you are an expert and be able to answer all these questions. When people ask you why these things matter, or some things matter and some things don't. So that's the reason why we're doing this. So then now what we want to know is the norm of this temporal derivative. Now let's imagine that we computed this gradient. So the gradient of the loss with respect to one of the HTs, right? And then there is a vector, right? The vector tells me for each of the dimension how I should change my value, so of the HT, in order to increase or decrease the loss function. And then perhaps I can look at the norm and then say that, that is how much my backpropagation procedure tells me I should change HT. Right? That's the norm, right? So the gradient or the velocity has two components, right? One is the angle, so which direction should I change? And there's a norm that is how fast I should change. Now let's just think about how fast the backpropagation procedure is telling us what to do. And then the interesting thing is that the how fast we should change is related, not directly same, as the how fast the HT, the output of the hidden layer times the T, changes when we change HT minus 1, the input to the HT, the layer. Let's see. I'm going to make some assumptions here. So I'm going to say that the nonlinearity is going to be hyperbolic tangent function. So it takes this input, let's say, the prime dimension, and then mapping to this interval, -1 and 1. So each of the dimension is going to be between -1 and 1. So the one particular example is the hyperbolic tangent function. This is one assumption I'm going to make. And I chose it just because both the output and its derivative are bounded from above and below. So for instance, in this case, it's bounded below from -1 and above from 1. And also its derivative, let's say the derivative of hyperbolic tangent, is also bounded from below 0 and then above 1. And then it kind of, let's say, makes it a bit easy to write the kind of analysis here. And now let's look at the norm of this temporal derivative. And this is the norm of the diagonal matrix, where the diagonal corresponds to this derivative of the nonlinearity times u. And then if you remember from one of the math courses that you have taken, Cauchy-Schwarz inequality. No. I had to look it up. I know this inequality, but I didn't know that it had this complicated name. But mathematicians have some issue with their ego, so they have to always name their, let's say, inequalities and theorems after names, their own names. Absolutely uniformity.
Shouldn't it dimension that after the non-linearity? So for instance.
Oh yeah, there should be T prime. Yes, sorry about that. Yeah, you're right. Yeah, so it's a Cauchy-Schwarz inequality, and then what this inequality says is that the norm of the product of two matrices is bounded from above by the product of the norms of those matrices or vectors. So what this Cauchy-Schwarz inequality tells us is that the norm of this temporal derivative is bounded from above by the norm of this diagonal matrix and the norm of this U. And then here, we're going to just assume that this, so this Cauchy-Schwarz inequality actually works with many different types of the norm. You can imagine, let's say, using a matrix norm. I think it even works for the Frobenius norm. But one thing we can do is that we can imagine that everything was vector as well. That's actually perfectly fine because we are anyway computing the gradient eventually. So we can say that those are all just flattened out vectors, in particular for the U as well as U, which is just a matrix, right? Which is a matrix, but that's just a collection of numbers. In a sense, the parameters we have is just a numbers from a gigantic vector. So you can imagine it like that always. Now then, if you start from here, so diagonal matrix that consists of all these, say, derivative of the nonlinearities times the norm of this U can be rewritten down as the next sigma square of prime AT. So we're using the matrix now in this case, so okay, but that's okay. So it all works out anyway. So we look at the norm of U, and then this is again bounded by the norm of U. Why is that? Because the derivative of hyperbolic tangent is bounded from above by 1. So it was a bit artificial choice, but because this derivative is bounded from above by 1, so this whole thing can be bounded by the norm of the U matrix.
Why is it equal to the max?
Max.
Why is it equal to the max?
Oh, that's just because we're using a matrix norm, if I recall correctly. I think that we decided.
Oh, okay.
Yeah, it's a choice of the norm. But the thing is that it really doesn't matter, choice of the norm, because we can always change this into whatever the constant we want. And then the constant will never be actually greater than the derivative of the sigma. And then that one is bounded from above by 1. So essentially, the important thing is that the norm of the temporal derivative is a function of the norm of the transition matrix. That's really important. And then the interesting thing is that the values of the actual HT we can control very easily by choosing a appropriate, let's say, the nonlinearity. If we choose the nonlinearity to be hyperbolic tangents, it's all bounded really nicely. If we feel adventurous, we can just use the rectified linear units. Whatever, we can control it. Now, on the other hand, in fact, controlling this U matrix is a bit of a problem. We don't know how to do it exactly. That is a reason why we're focusing a lot on this recurrent matrix U. And then the fact that the norm of the temporal derivative is a function of the norm of the U, in some sense, right? So we're looking at largely the upper bound, but it is a function of it. That actually tells us a lot about it, in a sense that if we now look at the norm of the Jacobian of the output, the prediction of our neural network with respect to HT, this one is going to be, because of the same Cauchy-Schwarz inequality, is bounded by the norms of all these Jacobians, starting from the very final layer, -1 all the way to the norm of the HT plus 1, HT. Then by using the results from here, we can say that we can bound it once more by saying that this is going to the norm of the Jacobian of F with respect to HT times the norm of the U, but that is going to be multiplied T minus capital T minus T times. So we're going to just try to multiply this over and over and over. because each and one of them is going to be bounded by the norm of the transition matrix. So we just replace each and one of them with the norm of the transition matrix, and then we see that there is a first one, the first one, that is followed by a lot of products, repeated products of the norm of the U matrix. And if you recall about the just numbers, right, in general, let's think about the positive number. If you think about these positive numbers, this is just a norm, so we get a scalar. If a scalar is repeatedly multiplied, what happens? When the scalar is 1, it's same as 1. If the scalar is slightly larger than 1, it exponentially increases towards infinity. If the scalar was slightly smaller than 1, it's going to decay exponentially towards 0 if you multiply it over and over. So what that means is that the norm of this Jacobian of what happens at the end of the neural net with respect to some of the layers, how big the value can be is a function of how far we are. And then how far we are, because that is capital T minus T, and the norm of the recurrent matrix U. So that's or the transition matrix or recurrent matrix U. Yes.
U's are different, right? At every step.
U are all same because we are talking about the recurrent network. It's the same U. So that's really important. And then there are many different things that can happen. If the norm of U, let's say there was a spectral norm, if the norm of the U was large, then we know that this norm of how much the magnitude of this change might blow up. It could be a very large number, and there can always be an issue. But that's fine. If the norm is too large, we're just not going to trust how much we need to change U. We're going to say that, yeah, okay, so the angle seems to be right, but the step that we need to take is probably not right. So we're going to just take a very small step, or we're going to just skip that step. So that's fine. And then that is what we call exploding gradient, and exploding gradient turned out to be not an issue at all. Gradient may happen. It doesn't have to happen, by the way. May happen when norm is greater than 1. And it's not an issue. It's not an issue. If you see that you compute the gradient as you do the back propagation, if you see that the norm is like blowing up, you say that something's wrong. We're going to either ignore that step, or we're going to just make the U a bit smaller generally. That's fine. We can always avoid that issue. Now, the bigger issue is what we call vanishing gradient. This is super problematic. Vanishing gradient happens when the norm of the U is smaller than 1. Smaller, of course, not just smaller than 1, when it's smaller than 1, and it is multiplied over and over, but then you had it over and over many times, right? All right, so the vanishing gradient, why is vanishing gradient an issue? Unlike the exploding gradient.
So you can shrink the U, right, for the exploding?
Yeah, in the case of exploding gradient, you're going to skip that update once because it's blowing up. You can either shrink U, or you're going to just try the next mini batch and then see whether it's going to blow up or not. Let's see, the exploding gradient is not an issue. And there are all those tricks like the gradient flipping and whatnot, all by default implemented, so do not worry. Not worried at all. Vanishing gradient, on the other hand, is worrying. Why is this a worrying phenomenon? Why is it worrying? So let's see, why it's worrying. So the vanishing gradient, you can imagine this as a phenomenon where the norm of the gradient of the loss function with respect to, let's say, one of the applications of the U matrix goes to 0. Or you can also think about, the entire thing goes to 0. Doesn't really matter, but this is an issue. This is the kind of thing that we see. But we can't really do much about it. And then why can't we do much about it? Because there are two cases where vanishing gradient happens. One is when learning is over. So we're doing the gradient descent, right? So we are doing the gradient descent. Let's say it was some kind of convex function. We're doing the gradient descent. And then as we get closer and closer and closer and closer to the bottom of this basin, right? Bottom of this function, gradient actually should, the norm of the gradient should go down. Eventually, we're going to end up with the actual minimum, where the norm of the gradient is just 0, because you have to be found the minimum. Now that's one case, and then that's a good case. Learning is done. We solved the problem. Optimization, perfectly solved. But the other case is that somehow it turned out that just the choice of the u, how you initialize u, turned out to be not that great, so that the norm or spectral norm or some matrix norm, spectral norm of u turned out to be too small. Turned out to be small. And then because of that, it's just the gradient just vanishes. Now we can't really tell the difference between this, the first one, that is the optimization well done, versus we're stuck somewhere, the gradient is close to 0 because we just initialize it incorrectly. So what does it tell us? Is that it actually implies a lot of things. One is that the neural net objective function that we use are never convex. It's not a convex function. And then depending on where we are, we may actually start or they get to a place where the whole function is super flat nearby. And then there can be number of let's say cases of the kind of flatness. One of them is that if we found the minimum, great, it's pretty flat minimum, perfect. Or that we just started from a wrong place, and then the place turned out to be a very high loss place, but with a very low, let's say, the derivative gradient. And unfortunately, we can't tell. We cannot tell these two apart from each other. So that's why vanishing gradient is a very big issue. And then what this actually tells us, in particular in the context of the recurrent neural network, when these things goes to 0, what it actually tells us is that these temporal derivatives or the product of the temporal derivatives are going to 0, is going to 0. Then what that means is that we cannot tell how to change the hidden layers values long time ago in order to change our loss value. And then that actually corresponds to the inability of this kind of recurrent neural net to capture so-called long-term dependencies. So what is the point of doing language model, if we just go all the way back to last week or week before, is to be able to tell what the next word is, right? So given all the previous words, what is the next word? But then we noticed that there was an issue with sparsity. So we decided to go for the Engram language model, where the n is going to be reasonably small, so that with a large enough data set, we can have the non-zero counts for most of the interesting stuff. That was good. Or if that doesn't help, we can always use the backup or smoothing. But then there was an inherent limitation. That is that it cannot really capture the long-term dependency. If you remember the example from last week, in Korea, more than half of the residents speak, then what should be the next word? Now, if I didn't see in Korea that is a further away than the usual n, I can't really tell whether it should be Korean, English, whatever the language you want to choose. But if I could capture the kind of long-term dependency, it becomes like super clear that it should be either Korean, I think it's has to be Korean, the Korean, right? So then we introduce a recurrent neural network that is able to read the sequence that has the unbounded length. All good, except it turned out that we actually run into the exactly same issue as the sparsity. But it doesn't show up as the form of the actual 0 counts, but it shows up as the fact that the gradient vanishes, this temporal derivative vanishes. So we cannot really tell what I should change in the hidden activation, let's say 10 step, 20 step, 100 step before, in order to lower the loss function. Now, in the example that we just gave, what should that be? The idea, what we should do is that if at time step, let's say 1, 2, if I saw Korean, right? Then what my neural net needs to do is to remember the Korean was there. So you can imagine that this is HT as encoding each of the dimension, encoding what has been seen before, right? What kind of, let's say, words appeared before. Now, one of the dimension is going to be assigned to, let's say, in Korea. Then I need to know that because the final one was supposed to be Korean, but I predicted as English. I need to backpropagate this error and then know that, oh, this dimension that corresponds to in Korea needs to go up. The value needs to go up. But then, unless this U is well configured, we can't really do that because it's going to vanish rapidly towards zero. So it turned out we avoided the issue with the sparsity by using a neural network and word embeddings. And we avoided the issue of the short context or the limited context by using a recurrent neural network. But we actually end up with a problem that is called vanishing gradient that actually defeats the whole purpose. We cannot really capture a long-term dependency easily. So, I mean, of course, if that were the case, then we wouldn't be able to actually do much. But it turned out that we can actually solve this problem. In 5 minutes, we're going to come back and learn about how to address this. All right. Yes, what I'm happy, so, the recurrent network is kind of because of linear.
Think about it, all this is transforming.
Oh, so if you have observations, there are many ways to easily you actually keep the delta as one of the features. Or you can use something called zero. It's like use the actual, but then we actually don't know the exact progress how we answer. So actually learn as a neural network. The actual input to the this is one like fill in all those or then simulate it until the next observation. Yeah, I mean, yes, I mean, it's exponential decay. Or for example, it can learn all those short right, oh, good. Diagonal is just
Trying to figure out the chapter.
All right. Okay. All right, not high school anymore, not high school anymore. Okay, so chit chat is for you at the end of the presentation. All right, so let's come back to this whole thing. And then, let's see, so we now know what vanishing gradient is. Now let's think about where the vanishing gradient comes from. The vanishing gradient, if you think about it, comes from the fact that in order to compute the Jacobian of the output, our prediction here on this prediction with respect to one of the layers, the earlier layers, we had to go through every single layer. We had to know what each and every single layer actually has impact. So we had to go through all those temporal derivatives. And because we're multiplying all these temporal derivatives, either small change is amplified or big change completely vanishes. And then you can imagine that this is some kind of a chaotic system in some sense, right? So and then you see one of the ways in which you can think of is that I don't know if you played this kind of game when you're a kid. Let's say your friends are going to make a line, and then you're going to start with some kind of sentence or the word, and then every time you have to pass the word to your friend next to you, right? They're doing all the way. At the end, you're going to try to figure out what word that was, right? And then maybe you played it in a noisy environments and so on, and then you do see really weird, let's say, game research. Right? So the issue there is that every time there is a pass of that information, there is some kind of, let's say, error that accumulates, or the information that accumulates. And then the information can accumulate quickly, or the existing information can die out very quickly as well. So that is the reason. If there is a reason, what can we do? Perhaps what we can do is that if the person at the one end who actually heard the original answer, if that person could just go all the way to the end and then told the final person the answer, that will actually solve the problem. You can just skip all those, let's say, steps. So what we can do is to introduce a linear shortcast. So what we are going to do is that the HT, so we're going to look at this one step of the recurrent neural net. That is the sigma of UHT minus 1 plus WXT plus B. But then I'm going to say that I'm going to look at all the previous time steps. And I'm going to use some GT. I'm going to transform this, let's say, all these HT primes with the GT. And this is equivalently saying that the HT is going to be sigma of UHT minus 1 plus W XT plus B plus sum all the previous ones in GT, then the copy of HT prime at T. So what have we done here? So this part is exactly same, right? This part is exactly same as before, but now we decided, so you can imagine this GT, just ignore it for now. You can say that this is just an identity function. That's fine. We're going to say this is just an identity function. Then what we do is that we're going to simply add all the values, all the hidden layers activations from the previous time step into what we compute at current time. We're going to just add them up. That's why we're going to call it linear shortcut, because it's going to be a linear function. So now, without this second term, HT was a function, and it's a nonlinear function of HT minus 1. And then every single value of H before T minus 1 had to go through HT minus 1 in order to result in HT. But now what we do is we're adding these shortcut connections. We're saying that let's say H1 could impact HT directly without having to going through HT minus 1, HT minus 2, all the way to HT. And then here I just use the bracket notation to make it a bit clear that we're using it over and over at every time. Now, what does it actually change? Let's look at this temporal derivative again. We look at the dt, dht minus 1. Oops. I'm going to now look at the ht prime, where the t prime is going to be smaller than ht. In this case, there will be a lot of, let's say, indices, right? So it's going to be a product of the temporal derivatives going from 1 to t minus t prime, ht dht minus d double prime plus 1, dht minus t double prime. So we are looking at the steps t and t prime. So we're looking at all those temporal derivatives. So that's it. So we just multiply all of them. But then, interestingly, because of the second term here, there is the linear shortcut connection. What we get is that we have the sum of the dht, dgt, copy of the ht prime of the t times. So this is much more confusing than I thought it was. But ht prime, use that t. Oops. Right, there you go. Over d ht prime, use the t. So let's see. What I'm going to just say that okay, t prime is smaller. Let's say very much smaller than t. Now, usually to compute this temporal derivative that spans many steps, it used to be just a product of all those one-step temporal derivatives, right? But then now, because we added this linear shortcut connection between now and every previous steps, right? In order to compute this, we actually have the second term in computing this temporal derivative that checks how the ht should change had we changed the ht t prime directly via this gt function only. And then if the gt function was just identity, then we'll just look at directly how the ht changes with respect to ht prime, right? And then this going to be just one, right? There would have been just one vector, right? Or the identity.
So, Professor, so the HTs are not just connected temporally they're also connected across, like,
well, they're still
HT1 and
temporal,
HT2.
right?
They're not just connected to each other.
Mm-hmm.
So is HT1 connected to HT2 and HT3 and HT4
directly? Precisely. That comes from this term, right? That's that that linear shortcut connection does exactly what you just described. Is that so the first term says that in order to compute HT, or the impact of all the HT prime where T prime is smaller than T on HT goes through HT minus 1. That's what the first term does. But now the second term, what second term does is that there is a direct, let's say, influence or the impact of HT prime where T prime is smaller than T on HT linearly via this transfer function GT. And then this GT might as well be just an identity function as well. So we're essentially creating all those short connections via which information can flow forward. Yes.
Can you explain the exponent T on the linear?
Oh yeah, exponent T is that now we have a lot of HT, we have H1, H2, H3, H4, but for each and every one of them, it's going to be directly impacting the let's say all the future HTs. Right? So you can imagine that we have one let's say HT, but that is being that is actually copied for every time it is being used. Just like what we use this bracket notation for the parameters in a recurrent network where the parameters were all shared across layers, right?
So at like T prime equals 3, we need to represent. So
when the T, let's think about T1. Now T1 is going to be used to compute T2. I'm sorry, H1 is used to compute H2, but H1 is also used to compute H3 via this linear shortcut connection. And you can imagine that every time it is used, we're making a copy of it. And that's what we did with the shared parameters in a recurrent network. Every time we use, let's say, recurrent matrix or the input matrix W, we're going to just make a copy. And then later on, when we do the back propagation and try to compute the gradient of the loss function with respect to those copied ones, we just compute all those things and then sum them up in order to get the gradient of the gradient with respect to the original one. So that's just a kind of being very explicit that is happening.
So I assume it's tried to just connect the previous H,
yep.
And it didn't work. Is that why you needed to connect all of them together?
Yep. So as you can see here, what was the culprit of this vanishing gradient is this repeated product of the temporal derivatives. So instead, what we do is that we avoid doing this repeated product and then compute directly what the impact of the change in HT prime T prime has on the HT. So that's the idea. Is that what is a way to avoid always going through this repeated product? Now you can imagine that let's say H2 is when we look at the in Korea, right? So that's the part that we have seen. And then now we are trying to look at what happens about, let's say, 10 steps later, where we need to predict that the next word is going to be Korean. Then now we know that so that the low probability assigned to the Korean should go up. Then I know it correctly. I should have actually changed the H2 so that this H2 actually encodes the information that there was in Korean in the early time. Right? I don't have to go through all these intermediate steps to carry over the information because the information might as well get lost. But this one creates the direct connection. Okay. Yes.
So you're saying G, T can be the identity function? Are there other functions you want to do?
We're getting there.
Okay.
Yes.
If the product causes a vanishing gradient problem, why do you still keep it there? Why not just use the second term?
Yes. So then why don't we just use this one? Right?
Or make copies each round, like you said.
Right, but if you notice here, the interesting thing is that this is essentially a backup word. Right? It cannot really capture the ordering information of all those previous H's. So to capture all those, let's say, sophisticated ordering information of how what kind of words or the phrases appear, we still need this kind of complicated nonlinear function. So we're essentially saying that anything that we can immediately get, right, by passing through the entire thing, if there were, let's say, simple thing all their own that can be used in order to make a better prediction, we're going to use a shortcut connection. But still, we don't know what those are going to be. So we have to have this one in order to accumulate the information, and then every time we run it, this is how we accumulate the information. But then this is how we're going to send the intermediate computation forward in the future. So we can't only do this, because I think this is how we actually capture all those patterns. This is how we send information to the future, bypassing all those steps. Is it not clear? Right? A little bit. So what this one does is the actual pattern recognition part. So we're going to look at, there were, let's say, really important 3 trigrams here. In Korea, right? In Korea, wait, so that's a really important bigram. This one is going to, initially, it's going to take as the input in, and then it's going to take as the input Korea, and then it knows that in was there. So the HT knows that in Korea was received. And then it turned out that we can now send this, whatever has been captured, that HT times that T, all the way into the future to the H capital T. And then the sending into the future part, bypassing or skipping all those intermediate steps is the second term. That is the reason why I was referring to it as linear skip connections or the linear shortcuts. It's a shortcut into the future. Yes?
How do you make sure that skip connections don't overpower the product?
So what if this one tries to do too much? That's fine. If that is how the problem should be solved, then we'll let it be solved. But that's the point of why we're using machine learning rather than just providing all those rules in order to solve the natural language processing. Is that we don't know what is the right way to solve it. We can't really tell. So let's say it turned out that the entire network is only relying on this part. Now, is it desirable or not? It's actually not easy to tell. If you knew already how to solve it, you wouldn't use machine learning to start. All right, any other questions at this point? If not, let's come down. And then obviously, one of the challenges of doing so is that if we don't constrain this GT, so this GT can be different for every time step, and then the number of parameters can grow. Then we don't want that. So we want to make sure that this GT of, let's say, I'll call it A, should be invariant to the time step. So we're going to use the same G everywhere for every, let's say, previous time steps as well. And then one particular case is called residual connection.
Is it an assumption or?
Sorry, what?
Is it an assumption, a restriction?
No, this is a constraint that we're putting. Is that we're using the same G at every time step. And then residual connection is a one special case where we say G of A is just A. So in other words, it's the product of the identity matrix to the input A. If we do so, HT equals sigma UHT minus 1 plus WXT plus B plus, okay, hold on. Yeah, so, okay, so let me see. I think I had a wrong, so okay, all right. I know it's going to be confusing, but it's fine because we're going to use just one G. Let me see. Yep. So then let's look at this. So what we're going to do is that in the case of the residual connection, now I'm going to look at this whole thing. And then in this particular case, we're going to say, hey, let's go for one at a time. Okay, let's go residual connection at a time. What we're going to say is that if the G T minus 1 A is going to be identity, while G T prime A is just all zeros for T prime smaller than T minus 1. And once we make this choice, then what we end up having is that it's going to be simply H T minus 1. So the latest one, we use the identity function. The G function that is applied to any time step that is further away than the immediate previous one, we say that that one is just zero function. So it ignores it. And then we end up with this formula where we have a usual nonlinear part that is doing the pattern matching, right? That is doing the feature extraction. And we simply add the value coming out of the previous time step. Yep. And then once we have this, we can try to expand this whole thing, right? So instead of writing the ht-1 here, we're going to write the sigmoid of the u-ht-2 plus wxt-1 plus b plus ht-1 and on and on. If you expand it all the way, so I'll just do the one step, because we know that this one is going to be sigma of u-h-t-2 plus wxt-1 plus b plus ht-2, and then we can expand this and on. Then eventually what we end up with is ht equals sum t prime smaller than equal to t sigma of u ht prime minus 1 plus wxt prime plus b plus sum t prime smaller than less than equal to t h t prime minus 1. Then what you see is here. This is the linear shortcut connection. When I'm trying to compute HT, I'm essentially receiving all the messages from the past, right? Every step in the past, and I just sum them up. And then this is also summing all those, let's say, patterns that have been matched. Right? You can imagine. So let's say I did my sigma was just rectified linear unit, and then what it does is that it tries to add the new word to what has been received. And then for each of the dimensions here, if there was something important by looking at this t prime prime so far, that is going to turn it on. Otherwise, everything is going to be just zeroed out. It's rectified linear units. By summing all of them, HT knows what kind of things have happened in the recent history, right? Because of the issue with the vanishing gradient, you can't really learn too much. But then there is a direct connection that comes from the past that tells us that there was an in Korea diagram at the very beginning, and then that can be useful at the very end.
Professor, just to clarify,
yep.
The 1h, so ht is connected to ht-1 in this formulation. That's it, right? It's not connected to every single one.
No, but
just by nature.
Yeah, but that has the effect of actually being connected to everywhere linearly, because it's linear summation. Now, as you expand it, you end up actually having this linear sum of all the previous steps when computing HT. Yes. Okay.
So are you supposed to have the left sigma over there?
Here sigma, yes. This one, yes.
No, I'm sorry, the actual summation. Is that supposed to be there?
Yeah. Wait, yes, because you had this one, they all, wait, hold on. I'm being confused myself actually. Yes, HT, I'm going to do it. Let me see. No, actually, you're right. So that summation doesn't have to be there. So it's actually either one of them, right? So either we have this, or we can have summation here, and then this one just disappears. You're right. So either we do this, or we can rewrite it so that we are actually summing all those the hidden states. That's your. And then you have a question.
Yeah, this seems like in the end there will be h1 there because there's not 2 times ht-1, and when it's being expanded, there will be no ht.
No, there will be h0. Right?
Yeah.
And then we said that the h0 can be just set to all 0 vector.
Yeah, but the blue part will only be left with h0 because all the other is being expanded.
Yeah. So you're talking about the when it's h1, right?
No. I mean, so in the after part,
yep.
You expand ht-1
yep.
to ht-2 and sigma.
Yep.
And you also expand. Yeah, so when you expand, the term disappear because you explain it is not way. So I think you have to do 2 times h minus 1. You have to times 2 to the h.
Wait, so what we get is that so you can think of this as this we have this, so here, let's actually rewrite it. Let's rewrite it. All right, I think that's a great idea. Okay, let's rewrite the whole thing. Just delete it for now. Now, so let's look at it. So HT is going to be sigma d minus 1 plus WXT plus B plus sigma of UHT minus 2 plus WXT minus 1 plus B plus HT minus 2, right?
Yes.
And then if I just write it once more, HT minus 1 plus WXT plus B plus sigma UHT minus 2 plus WXT minus 1 plus B plus sigma of UHT minus 3 plus WXT minus 2 plus B plus HT minus 3. And then we go on and on, right? All the way. And then what we end up with is that we get a T prime that is smaller than T, that is sigmoid of the UHT prime minus 1 plus WXT prime plus B, right? And then H0 is just 0. Yeah. So either we write it like that, or we say that this is a right, right? Yeah, let's just write it like this. The summation could be either one. We say that the H's are summed, or we sum all this. Okay, got it. Okay, all right. So what it's saying is that essentially whatever we do is we're always just looking at what has been already computed earlier. Look, and then we have to be careful. These are not independent summations, right? These terms within summations, they are not independent of each other because there is the dependency here. So what this H is, we have to be careful, but you do get the idea of this kind of linear shortcut, right? Now, the one interesting thing here is that you can actually explode in the forward path because of the linear summation. Why is that? Now, I want to look at the norm of this HT. And then again, using the Cauchy-Schwarz inequality, what we know is that this can be bounded from above by the norm, sum of the norm of the all these HTs. Right? And here, if you look at it, and then we never actually said that this norm is going to be this norm is bounded. You can always bound it, as we said. And the sigma can be just hyperbolic constant function, and then the norm of this vector is going to be bounded from above. But then we're summing them. So the maximum norm of this HT grows as the number of time steps grows. So the one kind of, let's say, difficulty in working with this kind of linear shortcut connection is that if we have unbounded sequence length or the unbounded number of layers, then it's possible that we won't be able to actually compute it because on the forward pass, we're going to actually end up with the values that cannot be handled by the computers, right? We're always working with the digital computers. And then the interesting thing is that the explosion in the forward pass is kind of, let's say, identical to the explosion in the backward pass, because whatever I change turned out to have the infinitely large impact, right? And then that's actually the norm of the gradient, right? So how much do I change in order to make the change? And it turned out that that's infinity. That means that the gradient has already exploded. So it turned out one way to avoid that issue, avoid this issue, so there is a forward explosion, is to start from here. I'm going to make a copy. Start from here, but we are going to make a small adjustment. The small adjustment we're going to make is that instead of simply summing them up, we're going to say that it's going to be UT. So this is the element-wise multiplication. times plus the 1 minus ut, again, element-wise multiplication, where ut is going to be another function, another recurrent layer, ht minus 1 plus wu xt plus du, and then we choose this nonlinearity very carefully, and then make it bounded from below by 0, and then bounded from above by 1. It's the dimension.
Why the four explosion related equation?
Sorry?
How do you, so you said that the normal HT is bounded by the sum.
It is bounded, but it's just summed. So as the number of steps grows, the maximum norm or the upper bound of the norm of the HT itself just grows, right? So it's not really bounded unless the length is bounded, but we're working with the unbounded length. So it's not really bounded. So each term is bounded, but because the length of the sequence can grow indefinitely, the actual norm of the HT itself is not bounded. So that could be an issue, but when you're working with, let's say, the fixed number of the layers, then it's not really an issue. You just make sure that the things are initialized so carefully, so well, that this kind of, let's say, forward explosion doesn't happen. And that's easy is when you know exactly the number of layers. And that's the reason why in feed-forward network or in the convolutional network, these residual networks are so popular and well used without any kind of anything but just the identity G, the summing them up, because we know exactly how many layers we need to run. Then we can control it carefully by controlling how we initialize the parameters. But unfortunately, when we think about this kind of sequence modeling, we often do not want to assume that we know the length of the sequence in advance. We always want to be able to build a system that is able to generalize to the length that is beyond what we see during training. And that's a bit of an issue because then not anymore the norm of this HT is bounded. And it's quite easy to actually experiment with this, and then you see that the whole thing blows up quite quickly. So what we do is we're going to say that how do we actually ensure that the norm is not going to blow up? Now, let's say we use this, let's just use another. I'm going to say H and then, right? Because they don't have, yes.
Just to clarify, when you're talking about like convolutional networks and stuff with the fixed number of layers, that's like you saying, because of that, we don't have to do this here. Or would you still?
Yeah, we don't have to do this here, yes. I mean, you can, but you don't have to.
Okay.
So, okay, so here what we did was that each and every dimension of this UT is going to be some value between 0 and 1. And then this sigma h is going to be chosen carefully. You can just choose, not carefully, but there's a hyperbolic tangent function that's going to have a bounded value. In the case of a hyperbolic tangent, it's going to be 1 and minus 1. Now, once we have that, and then we multiply one side with, let's say, ut, and then the other side with the 1 minus ut, and then sum them. So we're computing the convex sum of the two values that are both bounded. Then the resulting value is still bounded. What that means is that regardless of how many steps we're going to take this kind of, let's say, convex summation, we're still working in a bounded region. So this kind of, let's say, UT, which often is referred to as update gate. Update gate. This update gate is a way to ensure that there is not going to be a forward explosion. Now it does actually come with a bit of a let's say the downside, but we don't have to talk about it at this point in this context. So what this update gate does is that it's going to decide whether a particular dimension in HT is going to be updated with a new value, or is going to just carry over the value coming out of the HT minus 1 previous time step. That's the reason why we often call it update gate. I called it update gate, and everyone else is actually following it. But anyway, all right. So that's why we call it update gate. Now, of course, the question is, how do we actually determine what values this update gate should have? We don't know. So we're going to let our neural network figure that out automatically. So this one is going to look at the previous hidden state as well as the XT. So that by looking at this is a summary of the entire, let's say, sequence so far. It's going to decide whether each of the dimension needs to be updated or not.
So the update gate is 1, or let's say 0.
Yep.
Then you're losing information from that XT, right?
Yep, but this is per dimension, right? This is multi-dimensional. It's an LNOI, so it's a d-dimensional vector or the d-prime dimensional vector. So for each of the dimensions, it makes a decision. But it's not exact 0 or 1. It's some value between 0 and 1.
So when the UT is like close to 1, like all elements 1, you like forget anything you have.
Exactly.
But can you prefer something?
But it doesn't forget
earlier,
perfectly, right? But this is still
can you prefer to include more information in longer ago rather than like?
So if that is the case, then this part should learn to close the update gate often. Close it often so that the UT is going to close to 0. And then how do we do that? We don't want to do that ourselves because we don't know where there are long-term dependencies or short-term dependencies. We actually don't know. To know that in order to know them, we are actually training these models, right? So and then one way to kind of, let's say, encourage that kind of behavior in the early stage of learning is to initialize this BU, the bias, to be some negative values, so that the UT is going to be close to 0 at the beginning at the beginning of training.
So for example, if we got a sequence like A, B, C, D, and when we are looking at D, and we think A is more important than C.
But we don't know. How do you know?
But we can't, like, this model cannot handle this kind of.
It can. Yes, it can.
Yeah, because when you want to forget something, you need to forget anything before.
No. So the important thing is that these are all nonlinear feature structures, right? So all those things that we see are not, let's say, stored one dimensional at a time, and then we forget it. But these are actually these are coded in a multi-dimensional space. So it's not that straightforward. But yes, it can forget. But if it has forgotten that, what will happen? The back propagation procedure is going to tell us to open or close the gate, right? Because whatever has been forgotten should not have been forgotten. And then if the model does not forget it, then the loss value is going to go down. Right? So that's the reason why we can actually learn both of them simultaneously from the data.
So the bias should be initialized with 0 because?
No, I mean, you can initialize the bias to be something negative. Yeah, but you don't have to. No. All right. So then what that means is that if we just ignore the fact that using a sigmoid function or whatnot, so that this value can be between both 0 and 1, and it doesn't have to be sparse. But if you just imagine for now that this can be sparse, you can think of this as learning those linear shortcut connections that are sparse, and then you're learning the pattern of the connection, right? So far, what we've been thinking is that we fixed the neural net architecture, we're learning all those ways, but in some sense, this gating mechanism actually allows us to decide on the structure of the network based on the input, which is like super cool idea. I mean, generally so. It's a bit difficult to make them actual sparse, and then whether the sparsity helps or not. But this is a one way for you to imagine what is going on with this kind of update gate that is modulating these shortcut connections. Now, from here on, of course, if you want, you can actually go one step further, saying that what if I want to just ignore some of the signal coming from the previous time step, because I know that some of them are not going to be that useful. Then you can now introduce another thing. Then we're going to call it a reset gate. Carry it over, and then we're going to say that before this, we're going to RT. Again, the element-wise multiplication. The RT is again going to be sigma R URHT-1 plus WRXT plus ER, and then gain is going to be between 0 and 1. So what it's saying is that at each time step, maybe some of the things that comes from the previous time step needs to be just reset or forgotten. And then it turned out that the people are very creative. So there's been like tons of variants of doing all these things. But at the end of the day, this one or the LSTM, those two are the major variants that have been used for learning recurrent neural networks. So let's just go through it once more. So how did we start? How we started was, so actually, let me just write it as GRU or gated recurrent unit. So how we started was that we noticed the phenomena called vanishing gradient. And then what we noticed was that the vanishing gradient often happens because, and then what this vanishing gradient does is that if we are looking at the gradient of the loss function with respect to all layer layers, or the use of some parameters in the all layer layers, the norm of that gradient tended to vanish very rapidly. And then we wanted to see why that happens. The reason why it happened was because in order to do the credit assignment, we had to actually go through every single layer. And then on the way, the credits got diluted. We couldn't really tell, that's how all this things. So when you think about the money laundering, what is the thing that a lot of people do, or a lot of, let's say, rich people trying to avoid tax? What do? They create tons of networks of the shell companies all over the world, especially in tax havens, and then put all those money there, hide there. And then now when IRS tries to tax them, it's almost impossible to tell who actually contributed to those hidden stashes of cash, because it's going to be multiple rich people. That's the input. So we have a multidimensional input going through the network of all these, let's say, shell companies. And then at the very end, we have a bunch of, let's say, hidden stashes of cash. That's the output of our network. And then what IRS needs to do is to go back, follow through, right? Follow through. Which shell company contributed to this stash? And then which other shell companies contributed to this shell company? And then it needs to go through. But then on the way, the whole signal, this credit assignment, or in this case, that's a blame assignment, that gets diluted. And then we can't really tell eventually what was the actual credit that this one of the rich people contributed to one of the hidden stashes, right? And then that happens. And then that is because we have to go through all those one at a time, and then there is a long chain of those hidden layers. So instead, what we decided to do was, well, let's introduce the linear shortcut connection, right? If we introduce a linear shortcut connection, then we can actually bypass all these intermediate layers. And then one popular way to do so is residual connection, where we simply add the value directly from the previous layer into the current layer. And it turned out it works really well in the feed-forward layer network case, where the number of the layers is largely known in advance. But we realized that there is some issue with the forward explosion. So what we introduced was this update gate that controls the norm of the hidden layer activations as we go forward, and it still has it's still a linear convex sum. So we still can backpropagate all the error signal as far as we want. Without the issue of there is always a bit of an issue with the vanishing gradient just because it's a complex summation, but without the issue of vanishing gradient. So,
is there a difference between the H raised to the T-1 and H sub T-1, or
those are the same thing. Sorry about that. I always kind of do the same myself, but subscript and superscript, all the same thing, All right, so in fact, I realized that I covered only 2/3 of what I wanted to cover today, but we'll continue it from next week when we move toward the so-called attention domain. All right, practice is.